Okay, now it's working. So, I'm gonna share my screen for 1 second to just share the agenda. Um, where is it? So, we're gonna start chapter 6. But before starting chapter 6, if I recall correctly, Carlos has like one example or some examples that he would like to show us. I was thinking that maybe 20 minutes. I don't know if that's enough. Uh, Great for finishing the last details of the chapter 5, that is retraining on label data. And then after those 20 minutes, Michael will take over and introduce chapter 6, which is fine tuning for classification. All right, good.
Correct.
Charles, go ahead.
So let me go and share the screen. Okay, I'm sharing the notebook, right? Um, Let me move this part. Okay. So the last session, what we were doing is basically pre-training the model that we already built, and the thing that I did was all contained in this notebook, pre-training on the El Capo LLM from scratch repository. So this part, I'm not gonna cover it. I'm not gonna follow this one again yet today. I'm just gonna show it to basically recall what we did, and then I'm gonna go to another one, which is another version, a different version where I'm doing the same thing. I'm taking the model that we had from chapter 5, and I'm training it, but I'm doing it in a slightly different way. Rather than using this in this chapter, we were using this text that was something like a novel or something like that. And what I'm going to be doing is a different example, just because I'm trying to make the model even tinier so we can plot things. But what we were doing was we had the model already. We could train, we could do inference. And this chapter was about preparing some data. So that's what we were starting, obviously. Um, and in this, we had already these three parts. Sorry, we had already the data preparation and the attention mechanism and the LLM architecture. All of these from 1 to 3 were done. And what we were doing here was to start already pre-training on that data. So we had to prepare a training loop. I think that the most interesting part about coding was to care about the model evaluation, because we had to decide how we were going to decide to tell the model when it was doing right or wrong. So we created that cross entropy model, cross entropy loss function. And then we did this thing that I'm going to skip today, which was to load the pre-trained weights. It's already in the book, and it's on the in the video of the last session. It was basically about downloading the files, because the GPT-2 files of that OpenAI released, they were files made in TensorFlow. Then if we wanted to load them into our PyTorch model, we had to do some mapping. So there is a function, and it is both in the book and in this notebook at the end, and also in Sebastian's notebooks. So I'm going to skip that part, but this is just how we are going to leave the things for the chapter that we're going to start today. But what I wanted to do it today is to do a different approach, which is I call it this. This notebook is also on the same repository, by the way. If anyone wants to follow it on your own computer or something like that, it's this other one. The one that we did the last week was pre-training, and this one is called 12 Word World, because what I'm doing is I'm generating a vocabulary, and rather than using a chapter or a novel as our training text, I'm doing something much tinier. So I'm gonna be running the first self, because this is where I'm gonna the third party things that I'm gonna be using for this example is basically Torch, NumPy, UMAP for one of the plots, which I don't need to do that anymore, but because initially I was using embedding dimensions of, I believe, 6 or something like that. But then I had something, someone is drawing in the screen. I was initially using an embedding size of 6, I believe. It was just randomly. And then I found that I found that when I run the training loop, it was actually learning. So it was enough. So I shrinked it until I found that it still worked with 3, with a embedding dimension of 3. And I found that that was interesting because 3 is something that we can plot in space. So in this example, I'm actually using 3, and that means that I don't need UMAP anymore, but it's there. I mean, I didn't remove it, but we can use it if someone is following using the example. You can change the parameter. We're going to see that below, that we can use more than 6 as more than 3 as an embedding size, and this is still useful for the plots. But then Matplotlib, obviously, and IPyWidget, because there is a widget at the end that is interactive. So those are the three-party dependencies. And this is where I define the thing. What I'm doing is the text that I'm using for this particular training loop is just generating sentences from these 3 types of words, from these 4 adjectives. So what I'm doing is I'm generating randomly sentences of 3 words, like serene dream grows, or vibrant mountain flows. And the text that I'm using only contains this kind of sentences. Here I'm generating 100 of those, just separated by a space. And then I created a sentence, a function that takes an array like this one, which contains only sentences of 3 words. And what it does is it creates only one string from all of that array, separating it with the end of text, which, by the way, is a token that we saw when we were in chapter 2. But then in chapter 6, there is a mention of the end of token, but we didn't actually use it in the function that generates text. I will show it when we get there. So for the moment, let me just execute the cells, and that's what we have. This is the text that I'm going to be using for both the evaluation and the validation set. And right now, this is more or less the entire vocabulary, because I'm using the simple tokenizer. I'm not using the tick token tokenizer as we did in the other example, because in this case, let me jump to where I define the model. In this case, I want to have this very, 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 very tiny model. So this is the configuration that I'm using here. The vocabulary size, as I'm using the simple tokenizer, is only this number of words, of tokens. There is only 14. So the model starts the first and last layer only contains 14 tokens. If I was using the tick token tokenizer, it would have 50,000, both here and here. So it would be already like another order of magnitude. Right now, the entire number of parameters of the model is 177. So it's actually pretty tiny. I'm using here, as you see, the embedding dimension. This is, as I said before, I started with 6 and was decreasing the number until it worked. If I use 2, it starts being difficult for the model to learn even such a simple parameter. So 3, I think it's interesting because I'm going to be plotting the weights directly, which is what I wanted to do, plot the embedding space. And then for the rest of the parameters, I was decreasing parameters as much as I could. So at the end, I found that for this particular setup, I only needed 1 head and 1 layer because it worked. We're gonna see that I was using a bigger model and seeing that the curve was actually learning the patterns from this example. So I decreased until it was as tiny as I could make it. And then for the last example, this forward layer size, it's actually not a parameter that we have, but this is, if I go to the source code, when we created the feed forward layer, in the book, we hard coded a 4 here. It was the embedding size times 4, and that is hard coded in the book. I made it a parameter just because I wanted to, in this particular example, to make it even tinier. In the configuration, I am setting it, if I don't remember wrong, I'm setting it by default as 4, so it works. In all the project, it works as it did with the hard-coded 4. But in this particular case, I can go even tinier, just to make my only worry here was to make the model as tiny as I could, but still make it learn the parameter. So this is the entire size of the model. It has 177 parameters in total. And then this, I'm going to skip this part. This is just I'm storing some things in variables because then I'm going to plot the difference between these weights before and after training. So just going to skip the explanation of this. We will use them later. Now I'm doing what we were doing in chapter 6, which is, but just the only difference is I'm doing it with my text, which is very, very tiny text. And what I'm doing here is I'm reserving 90% of the text that I generated for the training, and the remaining 10%, which is this one, for the validation. So that doesn't have anything special. I'm creating the two data loaders in the same way. By the way, I forgot to say that I also chose very carefully the context length to be 4, which is the number of we have this kind of sentences where we have 3 tokens and then the end of token. So if I use 4 as the context length, then the data loaders that we're going to be using are going to basically use this as one of the steps, and then the next one is going to take the next sentence. So basically, I'm respecting the pattern, because otherwise, if I chose something like this, then I would be breaking the parameter when I use the data loader. So that way, I'm basically following the pattern. So the model only sees this pattern the whole time, which is adjective, noun, and verb, and then end of token. So what I wanted to check is that if I gave it an adjective, it will give me a sentence of 3 tokens. That's why I'm also using the end of token, because I wanted to be able to understand that what I want is an adjective followed by a noun and then a verb, and that's the end. So that's also why I changed the generation function. So, well, I want to show it now. Well, this is the same calculation that we were doing. The loader loss is the function that does this calculation. I cannot click here right now. Sorry. Is the I think it's here. Loader loss is where we are calculating the loss. So I have to go to it uses the batch loss, which is right here. And here is where we implemented the cross entropy. Basically, it's just a call to the standard cross entropy function from Torch. And we have initially these values before the training. In this case, that's something that Santiago showed the last time, depending on how your vocabulary size is. In this case, it's much tinier. So in the other example, we had an initial value of around 10. In this case, the initial value is tinier, but the thing that we're gonna be found, the curve that we're gonna find is more or less the same, although the initial, the higher, the start value is different. And now I'm also using the probabilistic text generator that we called it. And here is where I was mentioning this end of token. This is something that is actually from the book. This was already in the book, but if I'm not wrong, in chapter 6 we were not using it. We were encoding it, but not using it. I guess it was used then when we loaded the GPT-2 parameters, but in the example where you were manually doing things, I was a little bit worried because I didn't understand why we added this and then we didn't do anything with it. In this case, I'm actually setting the parameter to the end of text because, as I said, I want to check that if I gave it an adjective, it will follow by a noun and then a verb, and then it will stop. It won't generate anything more. So that's what it does. This is the loop where it's generating until the max token, which in this case, I don't care. I can set it to 4 or 100, but it will always stop at 3 because it must learn that there is a parameter followed by an end of token. So in this case, that's it. I don't know if I executed all the cells up to here. I'm going to run this one. And now we have the training loop. It's quite quick because it's just, I think that I'm setting 10 epochs because even with less than that, we would have it working. Now, let me just run these three lines, which is I can run it many times with one word as an input. And I'm basically seeing that more or less, sometimes it does not work, but most of the time it does. So it's basically a manual way of seeing if it works. I'm running the generation as I did before, but this time after the training. And now what I'm going to do is I'm going to do the same thing that we did before. I mean, we are using the same functions that we were using for the training. So it returns the validation and the train losses. So I'm going to go now to use this pretty much the same function to plot how it changed. So that's what I meant. I've been using this curve to basically decrease the model as much as I could. And now is when I'm going to start taking some of the weights again. This is more or less what I showed before, where I said that I was going to skip these lines. It was around when I instantiated the model here. I was skipping these lines. What I'm doing here is to copy these tensors to a variable that is stored in the GPU. That's because I'm going to plot. I'm going to be plotting them, so I need them in the GPU because it's basically the notebook, the one that is going to be doing that. And I'm using basically the initial prefix to say that these values are from are copies of the values before the training. So basically, we would expect them to be sort of random. And now, after the training, I'm doing the same thing. This is the token embeddings, which means the first layer of the model. And what I'm doing now is this is a function basically that I'm going to be using in the plot to add labels and identify from the 14 layer of the from 14 dimension of the let me go here. This initial token embedding layer, it has the embedding dimension here, which I set to 3, so I can plot it. And then this 14 is the 14 words of the vocabulary, the 14 tokens of the vocabulary. So I have 2 of them, which are special tokens. And then I have nouns, adjectives, and verbs. So what I'm doing here in this case is basically telling the system which ones are keywords, which are the end token and the unknown token, and then the 3 types of words that I have. Basically, so I can either set different colors or the labels. And what I'm doing here is I'm doing the first plot that I found that is kind of interesting. Here's what I was using the UMAP. So if you use a dimension that is greater than 3, you can use this plot yet, and it would shrink it to 2 dimensions. And what I see here is that before the training actually is random because it's what we're using, a random initialization. But if I go after the training, well, the keywords are not forming a cluster because they don't appear together. They used to be the 2 dots of the keyword. They used to appear randomly yet because they are not related. But the nouns are always together, the verbs are always together, and the adjectives are always together. So there is some clustering. But at this point, I wasn't really happy with this plot because I'm using UMAP. So it's kind of, I mean, it's showing something, But then I found that I could reduce the layers much more. So now I'm going to be using direct 3D scatter plots to do more or less the same, but without UMAP, because UMAP is moving the points. So this is not direct. If I run this cell again, we're going to see that the right side is different. We still have, actually, this time is not as perfect as before because there is some kind of something here between these two ones. But if I run it many times, we're gonna see that they always form something random at the left and more or less clusters in the right, but it's always different. So I wanted to have something more direct. I want to see directly what's happening in the layers. So I created these plots. So now what I'm doing is more or less the same, but directly as this I added after when I found that I could reduce it to 3 dimensions. So it's the same thing, only that I'm using 3D plots now. By the way, I have this problem. I have to, if I add this, I want to be able to drag here to move it. So I have to go and say widget. But if I do that, I have to do that for one particular cell. If I do that for two, I want to show you then what it happens. But this is a raw plot, 3D scatter plot of the weights before the training, and this is after. So right now we can see there is no UMAP here. So I can say here that there is a sort of a cluster in this part, a cluster of adjectives in this one, and a cluster of nouns in this one. Now I can say that they have been sort of pushed, especially if it makes sense, because in this case it's 3D. They have 3 dimensions, so I can actually plot them. Now I wanted to do something which is the same thing, but with the outhead. Just because I was curious, as both layers sort of have the same shape. They are both embedding dimension times the vocabulary size. Then I thought, okay, let's try to do the same thing. Let's try to see what's happening with the outhead now that I can also plot it. So I did the same exact plot, and I'm going to show it now. Here is what let me show you something, which is what I was talking about the widget. If I do this with the two cells at the same time, now this one says outhead rather than embedding. So I have to have only one cell at a time as widget. I don't know why. If I do it this way, now I can interact with this one. I don't know why, but it has to be only one. That's why I add these comments every time that I have a 3D scatter. But if you set that cell as widget, manipulate it, and then leave it again as inline, it works. So in this case, I'm doing the same exact thing, plot the outhead as it was initially, which again, it was also randomly initialized by Python. So again, I cannot see much of a pattern initially, but this is a surprise. There are also clusters in the outhead, which is interesting. And now I wanted to understand why. So that's more or less, we're getting to the end already. Well, I added some functions. If you check these, you're going to see that I'm using this called model enable debugging. I basically added a few stops in the model. Stops, I don't know how to call them. I added a flag called debug in the model, so I can set it enable or disable. And what it does is, if it's enabled, then when it run the forward pass, it creates an array where I have the values of the weights. Sorry, not the weights. The values of the outputs of each of the layers. So that when I run the token embeddings, I give it the input. It's stored a token embedding, which is going to be passed to the positional embedding. What I'm doing is, okay, but store it in a dictionary. So when I run an inference with the enable active, I can then check the values. So what I'm doing is I'm enabling calling an inference here, basically choosing an input text, a random combination of adjective and noun. I can also do that with only an adjective, for instance. It would also always work. And basically, I run the model and get the text back, so that now I can do also more plots. And in this case, I started focusing on the values of the last layer, because it's the one that actually determines what the next token is going to be. So what I'm seeing is that if this Serene Dream is randomly generated here by choosing a random adjective and a random noun. So here I have two tokens. For the first one, Serene, these are the suggested values. This is something that we saw in the last session. And what I'm doing also here is do the same thing for the other token. So this was for Serene, and this is for Dream, which is the second token. And in this case, it should be followed by a verb, which is also working pretty well. And now this was a question for me, because this is what we did in the last session, but I was wondering how it actually relates the specifics of probabilities for each of the words, how this layer, which contains only one, it does not contain a relationship between each of the embeddings and the probabilities. So I wondered how this this outhead layer was able to receive only 3 arguments, which means basically one embedding, which is enriched after passing through all of the layers, the attention layer and all of that. But I wondered how this layer can receive only, in this case, one vector of 3 dimensions and give it to us this thing. So basically what I'm doing here, just as a last exercise, is an interactive plot where what I'm doing, let me see if it works. I think that I have to go widget also. In this case, this is a plot of the last layer. I'm focusing only on that last layer. And what I'm doing here is there is an orange point called selection, which I can set the position here. So let's say that I want to see what happens with a noun. If to check that, what I'm going to do is I'm going to move the orange point so that it's more or less in the middle of the green points, which is the cluster for that. And what I'm going to do is I have to decrease the Y. So let me go there. And now on the X, I have to increase it a little bit. And on the Z, I have to maybe increase it a little bit. So basically, as I'm approaching the cluster, I'm seeing that what I have is the verbs. And I think that the idea here is that this is a linear layer, the outhead. Let me show it again in the model structure. As it's a linear layer, what it's doing is it receives a vector, which is the enriched token, and what it's doing is a scalar product of that, and then it's going to decide for each of the it's going to store different weights of so it's going to store, it has for each of the 14 features it has one vector, and it's going to do the product. So if the incoming vector has more or less the same direction, then this value is gonna be higher. But if it's very different, what means in this case, if the angle is closer to 90 degrees, then it's gonna be closer to 0. That is more or less what's that final layer is doing. So in this case, we can play with it. We can also, if we do that, we put the orange dot close to another cluster, we're gonna see that the values that get higher are the other ones, and this is the effect of the cross entropy that we did, which is to separate those values. And then I did one last thing, which is I wondered how the embedding was transformed. So I did another plot, which I'm not so proud of, but basically I wanted to see how the initial embedding. Let me put this one again as inline, because otherwise it's going to interfere with the last plot. So this last one, oh, I lost the control. Okay, it's back. This last one, what it does is I'm plotting the two tokens that I'm sending to here, which they were chose randomly. They are Seren and Dream. And for those two tokens, I think that the first one, Seren, is the red one, and the second one is the other one. Let me put this as interactive so I can basically drag. So what I'm seeing is basically the life of those tokens until when they get from the first layer to the last one. Most of the layers are either linear or matrix products. So in most cases, we're doing something more or less. I didn't expect this, but I think that we are if we start running this, even in more complex setups, we are very rarely gonna see very, very big angles here, because basically we are always doing products that are equivalent to the dot product, even if when we do that, like in the attention mechanism, where we do that in a matrix setup, but it's still dot product. So again, if we get with an angle, let me use angle because it does not make sense in greater dimension spaces, but in this case, it makes sense. So we are gonna get always something more or less soft, and it's basically moving from the initial vector, which would be something like this, and it's transforming it into a way that it actually, this is the whole process from, let me see if we can see the legend. This is all of the outputs from all of the layers. So each of them is pushing it so that at the end it has the dimension that produces the probabilities as the other ones in the same cluster. But it's also this. I guess this is what is actually doing also the same thing for the other tokens. I mean, we have a cluster that does not coincide probably on the first layer that in the last layer. They are in different position and probably not even in the same way, because they start with different random patterns. So we don't have to expect them. If I plot the first layer and the last one, we're going to see clusters, but they are not in the same position, but the process is going to basically connect the first one to the last one. So this is basically it. I wanted to see that this way because I wondered when we did the last chapter, I found that I didn't sort of understood how things were working. So this is a little bit of a step. There is still a lot of questions. Basically, this does not represent at all what a real GPT does, but it kind of connects the calculations, the code that we did to a real, very, very tiny but real example.
Very cool. Very cool stuff. Yeah, I was really happy to see the clusters. Like,
Yeah.
yeah, like the clusters are pretty fun that even with a tiny data set and a tiny model, you can see how verbs and adjectives and all of those are like clustered together. Very nice example.
I have to say one
Mhm.
last thing just to finish. I found that in this particular example, the feed forward layer, it was not playing an important role because I set the size to 0. That variable that it was initially for, I set it to 0, and the system still works. I think that as it's a layer probably intended to store facts more or less. In this case, the patterns can be deduced strictly from just where each token is, so it does not contribute. Probably if we have real text with very different sentences, it starts doing something. So
Nice. Thanks, Carlos. So now we go ahead with Michael, that he will be explaining us chapter 6, if it's right.
Sure. Thanks. Let me just share my screen. Okay. Is everyone looking at my notebook here in VS Code?
Yeah.
Yeah, so thank you, everyone. Thanks for letting me lead this discussion today. Yeah, I'm gonna go through chapter 6 and just kind of talk through the code in this notebook here. This is VS Code. That's why I like to run my notebooks. So yeah, chapter 6 is about fine-tuning, but especially fine-tuning for classification. So there's a couple of things that we're going to cover. Just talking about the different approaches for fine-tuning, preparing a data set, how we modify the LLM to get it to fine-tune. And then we have the specific case of looking at spam messages and how we can teach the model to do the specialized task of spam classification, and then how we evaluate the model for accuracy, and then we'll use it to do some real or give it some real examples of spam and non-spam. Some of the things that came up for me, just some thoughts that I wrote down is this felt like probably the easiest chapter in the book, but it does build on a lot of what we've done before. So I think it's quite important before you kind of tackle this chapter to understand everything else that we've done up until now, because it's going to be hard to kind of see how it all kind of fits together. And I also think it's really practically useful, this chapter, because I think in real life situations, often you're not going to have to pre-train a model from scratch. It's a lot more useful to take model weights that have already been pre-trained and then using it downstream for tasks with classification, either instruction tuning or classification like this. And a lot of what we did in this chapter isn't really specific to language models. Like it's just basic machine learning, setting up a way to evaluate your model, looking at the loss curves. So all of this can apply to actually lots of different data science and machine learning kind of use cases. And then I think there's just a couple of small things that stood out to me, big ideas that or key things to understand, and I'll talk about those as we go. So some of the big ideas was that we can fine-tune LLMs, and what that means is it's a way to teach them some narrower kind of task that they can do in a smaller domain. And the way we do this is by adjusting the architecture and then training it on a new set of data. And that this data set probably looks a little bit different from just a raw text corpus. And then there's two kinds of fine-tuning, classification and instruction tuning. For classification, I think the big idea for me is that what we're doing is we're taking this big vocabulary and replacing it with a much smaller vocabulary. And I'll talk about that a little bit later. The one thing to understand is that unlike before, we're only looking at the final token in our context window, and that's what we use to make our classification decision. And then we usually don't train the whole model. We typically will train only parts of the model, and I'll show you what that means a little bit later. And then there's like two metrics that we're going to be looking at. Like before, we were looking at cross-entropy losses as kind of our metric that we use to train the model, and we're going to keep doing that because it's a differentiable function. But we also have this other metric, accuracy, which is actually what we're most concerned about, but we can't optimize that directly. So we're looking at both these metrics. So in the book, the author quickly introduces us to the idea of fine-tuning. And there's like these two kinds of fine-tuning. So instruction tuning is that's this diagram here shows us that it's a way to take this data set of instructions and responses to instructions, where we're basically teaching the model to act sort of like a chatbot, where you're giving it these instructions and then teaching it how to follow those instructions and make use of all its knowledge and natural language understanding to kind of complete these tasks. That's a little bit more complex, and we'll talk about in the next chapter. But what we're doing here is something simpler, where we don't give the model instructions. We just teach it sort of these simpler input-output pairs, where we give it some input without instructions and teach it how to respond with this small vocabulary of tokens that basically represent our classification classes. So the way that we're going to go about this is we're going to go through these steps. There's like 3 stages and 10 steps. There's quite a few steps, but as we go through them, I'm going to just jump back into this diagram here and just kind of like cross out the steps, and then we can just sort of keep track of where we are as we go. So the first step you'll see here is to just download this data set of spam that we just get from the internet. So I'm going to run the cell and just inspect the data set, and you'll see it's a pretty simple data set where we have just 2 columns, just some text, and then a label, which is either spam or ham. So that was pretty simple. That's step 1. Just cross that out. So the next step is to prepare the data set for training. But one thing we'll notice, and often when you're going through these data sets, it's a good idea to inspect it and kind of look at the distribution of things, but we can see pretty quickly that it's unbalanced. So what that means is that we have many more examples of ham messages compared to spam. And the reasons this can be challenging is that your model might learn to sort of be biased towards just the one class. So it's easier for the model just to say everything is a ham message, rather than actually learning meaningful patterns and being able to discern what's real. So the simplest way that we address this in the book is just to undersample. So basically, we're just taking the same amount of ham and spam messages, and this is what this code does. I'm not going to go through it, but it's pretty simple. We're just basically making sure that we get a random sample of both classes. And then as we inspect it, we can see the data set is balanced. There are other ways to deal with class imbalance, and I think in the appendix they talk about that. And then so go ahead.
Yes, just one comment. Can you make the zoom of this a little bit bigger?
Yeah, sure, of course. Is that better?
Yes.
Okay.
Yeah, well, maybe a bit more if it is not too comfortable. Yeah, that at least in my screen, that's perfect.
Okay, sure.
Cool.
Yeah, I should have done
Thanks.
that. And then the next step is these labels are strings, but deep learning models or machine learning models in general, we tend to work with numbers. So what we're going to do is just convert the text labels into zeros or ones, and that should be our labels that we can train on. One of the key insights here is that, like I said earlier, what we're doing is we're taking this, our token IDs in this case are going to be just ones and zeros. So instead of this big vocabulary of around 50,000 words, we're going to start dealing just with these 2 tokens, 0 and 1, and our outputs at the end are going to just be one of those 2 classes. This random split method, what this is supposed to do, like instead of what we had in the previous chapter where we had like training and validation, we're going to make a slight tweak and also have this test set, which we hold out. We're not going to use that at all until the end to evaluate our accuracy. So all this does is it it takes these three, it makes these three splits in our data set, 70% for training, 10% for validation, and then keeping the rest. And then we save those to CSV files. I'm just going to run this. And then I think that takes care of step 2. So we've pre-processed our data. And so the next step is to create data loaders. So this is also something you should be familiar with from the previous chapters. We're using PyTorch's data loaders to be able to load our data for training, and to be able to have these sets of inputs and labels that we can iterate through. One of the things that we have to take care of before we do that is to think about, because our text that we're inputting into each example has a different length. We have to deal with that because our model needs inputs of fixed size. So there are different strategies that you can use here, but in the book we use this idea of padding, we've briefly kind of talked about this end of text token before, but it wasn't clear like how we can use this. But what we're doing in the book here is that as this, let me just zoom in here into this diagram. But what we're doing is we're taking our largest input and sort of saying anything that's smaller than that. What we'll do is we'll fill in all the empty spaces. So all of the sequences that are less than the largest sequence, we'll just pad them with the special token, which it represents as end of text token. But in our vocabulary, it's this token ID of 50,256. So we'll just kind of like fill in all of those empty spaces and pad those tokens so that the model can deal with these fixed input sizes, and these special tokens just represents basically the end of the sequence. I just zoom out a little bit again. So this code just shows us that indeed that if we pass in this end of text token, that's a token ID that we can use. So then we can go ahead and create this this data set class that what it does is it can take a CSV file, a tokenizer, an optional max length that we can set, and then we hard code this pad token ID. So what it's going to do is it's going to encode our inputs or the input text as tokens. If the max length isn't set, we'll get the max length. So we'll look at the largest input in our data set and what its size is. And then if the max length is set, we'll just use the one that's input, and we'll truncate all of the sequences that are longer than that. But then this is the important part where we do the actual padding. So here, what we're doing is we're saying that for all the sequences that are less than our max length, just fill in all of those empty spaces with this padding token. And then, like before, we have to implement this get item method for our data set to be able to index into our data. And what we're doing here is just returning tensors that could be used for training. Please stop me at any point if you have any questions or thoughts. So now that we have this data set, what we can do is we'll instantiate an instance of it. Oh, let me see what I didn't run this cell yet. And then we can see in our training data set, the max length is 120. So the largest text that we have is 120 tokens. So what we'll do then is we'll also create a validation and test data set, but we'll use the largest or or the max length of our training data set to make sure that we truncate any sequences that are longer in these two splits of our data to make sure that they're all the same size. So after this part, we can instantiate our data loaders. So we can make use of these data sets and create a data loader. And all of this, what this data loader is doing basically is it's gathering together, or we can create these input data input examples with that are all padded, and then get a class output for each of those inputs. So I'll just run this. And if we look at the code, it's fairly simple. We just pass in our data sets. We use a batch size of 8. So we're batching to 8 examples each. Num workers is just something that you can use if you want to be able to make use of more of your cores, make loading data faster, but for our tiny data set, it doesn't really matter. And then we just verify that everything works. So we can look at the dimensionality here. So we can see in our input batch, we kind of have what we expect. We have batches of 8 with an input of 120 tokens each. And then in our output, we're basically just having, in our labels, we just basically have 8 tokens. And then we'll print the total number of batches. So we have 130 training batches, and we're looking at 19 batches for validation. So that takes care of step 3. And then we can move on to stage 2. So we'll start by initializing the model. So again, this makes use of a lot of what we did before. We set up some configuration. We'll choose this GPT-2 model, which we'll use in the notebook, but we can also play with some of the other models if we want to. So we have the same configuration as we had before. We just set some of the model size specific config, and then we have this base config. Since we choose this model, we can create our base config with the overrides for this specific model. And then there's just some code to make sure that everything is set up correctly. And then again, making use of a lot of the code that we had before, we had this function to download the pre-trained GPT-2 weights, and then load them into our GPT model that we defined in the previous chapters. So we'll run that. Everything should have been downloaded already. And then again, just to make sure everything works, we pull in some functions that we used before to generate text and to convert text to tokens and back. We start with this beginning prompt where this sentence is every effort moves you. And then we call generate text simple and ask it to complete this prompt with 15 new tokens. And it generates coherent text. So one of the things we do before we actually fine-tune is let's just try, prompting the model just to see if we try and use it as an instruction-tuned model, what would it do? So we're giving it this prompt and we're saying, is the following text spam? Answer with yes or no. and then we give it an example of some text. If we run this, we'll see that the model is actually not really doing what we're expecting it to do. So if you've used ChatGPT, you would be able to, use this as a prompt. But because this model is a raw, untrained model, it hasn't been instruction tuned. So it's not really answering a question or a query. It seems to just sort of repeat the text that it saw before. So this is, typically why you would want to, or sort of the motivation for why you would want to do classification tuning. So that takes care of two steps. We have initialized our model and we are loading the pre-trained weights. So here comes sort of the important part is the next step is to modify our model for fine tuning. And even though there's a lot to take in, this is actually reasonably simple. So the first step is to add a classification head. And I think this diagram does a pretty good job of kind of explaining what we're going to do. So before we had this, our output layer, is our whole vocabulary. And basically we are outputting, a probability for what the next token would be given a sequence of input tokens. But since our vocabulary is pretty large, it's 50,257 tokens. That's the size of our output head as well. So instead, what we're going to do is take this whole thing and we're going to replace it with this single layer, which is just 2 tokens. So we're just collapsing down this big vocabulary into a really small vocabulary. In the book, the author also mentions that you can actually use a single node, but that changes our loss function. And that's actually something interesting to dig into if you want. But what we can do instead is we're going to still just have 2 tokens. So the way that we go about it, well, in the book, the author kind of shows us if you run this, you can look at what the model looks like. And we can see that we still have this fairly large output head. And before we go ahead and replace this, what we want to do is freeze all of our model parameters. So what that does is it basically tells PyTorch that we don't want any of our model to be able to retrain. So before we add anything trainable, we're going to make sure and freeze everything else. And the way we do this is to iterate through our model parameters and call this set requires grad to false. So now that we've done that, we're going to go ahead and take this last layer and replace it with this this layer where we only have 2 classes. So just setting a manual seed so we can produce it, and then we replace what we had before. So if I go back and run this operant model again, you'll see now that this has been replaced by a much smaller output layer. The author also notes that what you can do is that since we've frozen all of the layers, you can go ahead and just fine tune the last layer. But through experimentation, it seems that we can get much better performance if we also make some of the layers of the model trainable. So what we're going to do here is we're going to take this this final layer norm and the last attention block and make both of those trainable as well. So this is what we do over here. We just grab the last block here and then this final layer norm over here and set requires grad 2 on both of those. So we can still use this, the same way as we did before. And this is what we're showing here, is that we can still have this model complete our input tokens, but it's going to give us a much smaller output size. So we'll just start with this prompt of saying, do you have the time? This unsqueeze, what it's doing is just basically adding a batch dimension. And then if we run this, we'll see that we also do this part where we do the outputs. We can see that now our output here is one batch of 4 tokens of dimension 2 instead of 50,000. So this is also, I think, what this diagram shows, where we only have these 4 tokens. But there is something important to understand here, and this is also for me a key insight, is that for this specific classification task, I think this diagram actually shows this well. We do have 4 tokens that we're looking at because our context size is 4 tokens. But for classification, the token that actually matters to us the most is this last token. And the reason why is because it has more signal about all of the other tokens that came before. So for classification, we're going to kind of slice into the outputs in this way. And then we can basically use this last token that we're looking at here as our probabilities of each class. So this is, I think, a kind of a key idea to understand, is why, because of the way that attention works, instead of like the way before we use the loss of all of these tokens, but because of the way that we want to do classification and only care about this last token, we're also going to adjust our loss metric slightly, where we are only going to care about this last token. And I'll show you that in a minute. So yeah, that's how we modify a model for fine-tuning. And I think this is kind of the most important part of the whole chapter as well. So the next step before we can start training is to implement some way to evaluate our model. So if you look at this diagram, what it shows is kind of like roughly what we'll do. We input some text. We look at this last token. We get these logits. We can convert those to probabilities using softmax. And then we can take the highest probability class and use that as our predicted label. So again, here's an example of that. So what we're going to do is we take this last output, do softmax on it, get the index of the highest probability logit, and then use that as our class label. Although, this is one way we could do it, but if you might notice that we actually don't need to perform the softmax, and it's slightly optimal to actually skip that whole step, and we can just take our largest logits. So this code does that. It's pretty much the same thing, except we skip the softmax. We can just grab the logics directly and get the index of the highest probability one and use that as our class label. So now that we have some way to be able to do classification or get this class label, we can then use this to calculate accuracy. So accuracy is a very simple metric. Basically, we're just looking at all of the examples that we are evaluating, and how many of those we predict the correct label. So just that ratio is our accuracy. So what this calc accuracy loader function is doing is calculating accuracy using this mechanism to get our class labels. So I'll quickly step through the code. Model eval, if you recall, what that's doing is just setting the model into non-training mode. We initialize these variables to count the number of correct predictions and the number of examples, and then we'll use that at the end to calculate our ratio. If we have this num batches parameter, and that just allows us to calculate the accuracy on a smaller number of batches if we want. So if that is set, we just make sure that we grab less of those batches. And then in the main loop, what we're doing is we're iterating through our data loader. So what this will give us is an input and target batch pair, and then we loop through each batch. This is important for us to make sure that we're running on the right device. We use this torch nograd to make sure that we're not updating our gradients in the model. And then we can get our logits by passing the input batch to the model. And then, like I mentioned before, we're only using the logits of the last output token. We can get our predicted labels using argmags. And then we increment the number of examples we've seen. And then we can finally calculate the number of correct predictions by looking at how many of the predicted labels are the same as our target batch and summing those together. And then at the end, we will have in these two variables that we're collecting, we'll have the total number of examples and then the total number of correct predictions. We can just divide those.
Could you repeat again the difference between the input batch and the target batch here? So, like, are we targeting it for a particular GPU, or like, are there two devices involved here?
Do you mean this code?
Yeah.
Yeah, so device is just either running on GPU or CPU. So you just want to make sure that your data is on the same device as the model for performance reasons. But what input and target batch represents is input batch is our sequence of input tokens, and target is our label.
Okay. Yeah, that makes sense.
Any other questions? Okay. So, and this is actually, it's great that we're going on to the next step here. We actually, we are using this device. So the reason we have to kind of pass it through is at this beginning, I'll set it here in one place. This is slightly different code from what we had in the book because I'm running on a MacBook. So I actually, you'll see if I run this, I'm using this MPS device. But if you have a GPU available, you could probably use CUDA or just run on the CPU. It's just slightly faster to run on GPU and MPS. So we can use Torch to see if the device is available and then set it. And then make sure that our model is running on the same device. And that's also why this code is important, because then we can make sure that the data the input batches and target batches are in the same device as the model itself. We'll set a manual seed again, and then we can use this calc accuracy loader function to calculate the accuracy of 10 batches. So that's important to understand, not the whole data set, but we'll calculate accuracy on our training, validation, and test sets. Remember, at this moment, we haven't trained the model at all, so we're not expecting it to be great. So I'll run this, and indeed, you'll see our accuracy is not great. It's actually worse than just random like guessing. So that's what we kind of expect, because the model it's not really fine-tuned yet to be able to do spam classification. So some of the key insights here to remember is that accuracy is not something that we can directly use to optimize our model, because it's not a differentiable function. So we still use cross entropy loss the same way as we did before. And what we're doing is we're assuming that as cross entropy loss goes down, our classification accuracy will go up. And generally that is a good assumption to make. But it is important, I think, to understand that both those metrics are important, but cross entropy loss is kind of a proxy for this accuracy metric. So we have this calculate loss batch function. It's very similar to what we did before in chapter 5, but there's one important distinction to understand, is that instead of before, what we had, it was basically this is what the function did. It basically calculated the logits for all of the tokens in our output, but instead we're just taking the last token. So this indexing code that I showed you before. So we're calculating the loss only on the last token, but everything else should be similar to what we had before. And then this is also a function. It's the same as what we had before in chapter 5. It can calculate the loss for us on a data loader. And there's just some code here to deal with edge cases, like if the data loader is empty, we return not a number. And then we have the ability to also calculate loss on a smaller number of batches. So same way as we calculated accuracy before, we'll go ahead and calculate loss, the initial sort of loss on our data sets. And what is interesting to me is that I just noticed that earlier when Carlos was showing us his example, I think the losses that he calculated there initially was kind of similar to what we have here as well. And I think it kind of makes sense, because we also have a much smaller space of our vocabulary size is much smaller as well. Okay, so that takes care of our next this step of implementing some way to evaluate our model. And then we can move on to the last step, which is or the last stage, which is to fine-tune, evaluate our fine-tune model, and to actually use it. So these steps are together sort of in a notebook, but fine-tuning and evaluating the model is what we'll do next. And I think this diagram kind of explains it pretty well. So these are sort of very much the same steps as we had before for pre-training, with a few small tweaks. Basically, the one tweak that we're making is where we'll be calculating accuracy as we go. And instead of outputting, like, I don't know if you recall before, we used to output like some completions every time or every few snapshots. We're not going to do that here, because we are the we're not basically predicting the next token, we're doing classification. So I think this train classification simple function is good to kind of step through. So I'll kind of just walk through the code a little bit. We initialize these three lists to keep track of our training losses, validation losses, and calculate our accuracy and on training and validation for each epoch as well. So if you're not aware of epochs are basically, same thing as we talked about before, but the number of epochs are basically the number of times that you iterate through your training data. And that's something that we can specify as a parameter. And then similar to what we had with pre-training, we have this main training loop where we iterate through each epoch. We set the model into training mode. We can iterate through our train loader like we did before, get a input batch of the sequence of tokens and a label. We reset the optimizer. So for each iteration, we will reset the gradients from the previous iteration. We can calculate our loss. So we are basically making use of that function I showed you before that calculates the loss. Remember that this is going to calculate loss only on our last token. Then we can calculate the gradients for that loss and then update the model's parameters based on the gradients. We will, for each example, we will increment this example scene variable and the step that we're on. And then this eval frequency basically sets how often we want to output some evaluation metrics. So whenever we output the evaluation metrics, what we'll do is we call this evaluate model function, which is actually defined here. This is also from chapter 5. And basically all this is doing is it's calling calculate loss loader on this model that we have at the moment, and it will append those losses to those the two collections that we initialized up here, and then we'll print which epoch we're on, which step we're on, what is the current training loss and the current validation loss. And this is also done for, I believe, for a smaller set of batches. So this val iter will specify how many batches we'll calculate it on. So this is for each iteration that this runs. Go ahead.
Michael, yeah, I have a question. Why is it that we always reset the loss gradients after each iteration? That's a part that never, it always gets me confused, because I would think that you would keep the gradients, so you keep updating them, but I never understood that, just that little part.
Yeah, that's a good question. I think it comes down to some of the deep learning theory, but the basic way I understand it is that if you don't reset the gradients, it's not numerically stable. So basically what's going to happen is that the numbers will grow larger and larger over time, and you might end up with overflows where the numbers become so big that you're basically exceeding the size of the how many bits you can store in a like a float, for instance. So typically what you'll do is you reset, and this is not specific, I believe, to language models, or it's typically in a deep learning training loop. The best practice is always to reset your gradients. I don't know if there's anyone
Thanks,
else that
Marcus.
has a better answer for that. But I mean that could be an interesting experiment to try is to do the same loop, but maybe just take that code out or comment it out and see what happens.
Mm-hmm.
Could be an interesting, fun experiment and good learning opportunity.
Nice. Thank you.
Okay, so again, this is all happening on a iteration level, but then we also have some code to calculate our accuracy. So we will output our loss, but we also want to keep track of how our accuracy changes over time. So for each epoch, we're going to call this code that calculates the accuracy and then prints out the accuracy as we go. And then we append it as well. And at the end, we return all of our training losses that we calculate for each iteration, all of the validation losses for each iteration, and then our accuracies for each epoch, as well as the number of examples that we saw. So I think, hopefully some of this is familiar from some of the previous chapters, but I think it's also important to understand what's different. Basically, to me, I think the only things that are really different is that we are calculating accuracy as we go. And then it's also important to understand that we are, when we calculate our loss, we are only using the last token because we're doing classification. So we just need to run this evaluate model function as well. So then
What's the global step parameter here? I think so.
a global step. So basically that is just how many steps we've done. And that's just for us to be able to output it. I think here we can show how many steps how many times we've iterated through our training loop.
Okay. So what should be the recommended global steps here?
Well, yeah, that's something that is it's discussed in the book. Well, it depends on how many epochs, and well, it's a combination of how many epochs you specify and your batch size. There is no magic formula when it comes to choosing epochs. What the author recommends is that you start with some sort of common sense number. I think he's mentioned 5 as a good starting point. But then what you'll often do is you will look at loss curves. So as you're training, let's say you try 5 epochs, look at how the model is performing. Is the loss function going down, and then also look at how loss, your training loss and validation loss, plot both of those. And if you see that it seems like the model is overfitting, meaning that your training goes down but validation it isn't following, that is a point that you might want to stop training because that means the model is overfitting on the data set. But if like you see that it seems like the loss could still go down, maybe you want to up how many epochs you have. And then batch size is I think usually more related to how your performance. Like if you it's probably always better to use a larger batch size if you can, if it doesn't slow down training too much. So those are the 2 kind of parameters that you want to play with.
Yeah, that makes sense.
Okay, so now we can actually go ahead and do training. So as we did before, we're going to use the Atom W optimizer. So we initialize that with this learning rate and weight decay. These are also interesting hyperparameters to play with. During training, you can change your learning rate and weight decay to see if that improves training performance. We set number of epochs to 5, like the author was suggesting. And then we can call train classifier simple, passing a model, our loaders, this Atom Optimizer, the device, number of epochs. What we're saying is for every 50 steps, we'll run that evaluation loop that I showed you before, and we'll evaluate on 5 batches. So since I'm running MPS, I think I can actually run this. It should train pretty quickly, should run within a minute. And as we can see from our outputs, we can see that the loss actually goes down pretty quickly, which is good. And then every 50 steps, we're printing our accuracy, which is also going up. So we go from 70 to 82%. Then we hit 90% for both training and validation. 100% training accuracy, 97 validation. And then, yeah, training complete, and we get to 97.5% validation accuracy. I'm not going to go through this plotting code. I think it's something to look at yourself, but like we did before, we're going to use this to plot our training and validation loss. Oh, sorry, I ran this wrong. I have to actually run this again. And then we run the cell afterwards. Just so I can prove to you that training runs fast. So, oh, this is not expected. Huh. Might be because I trained the model twice that I broke something. I'm going to restart and run everything up until this point.
Yeah, while this executes, I want to make a question. I don't know if anyone is familiarized with TensorFlow callbacks, which is if you want to do something like, let's say that rather than choosing the number of epochs, we wanted to do something like, okay, train until you get to a 90% or something like that. I know that in TensorFlow, there are functions that you can define and pass it to sort of the training loop. But in this case, it seems like PyTorch sort of doesn't have those callbacks. It's more like you have to basically implement the training loop. Is there something like that, or is that an actual difference of the environments, or maybe there is some sort of callbacks also in PyTorch? Does anyone know?
Yeah, from what I know, you have to implement yourself in PyTorch. I'm gonna Google to see if there's some output like that.
Yeah, sorry for the delay there, but this is what I expected to see. So similar to what we saw in this output here, we can see that our training loss drops pretty drastically along with our validation loss, and they kind of stay the same. This is what you'd like to kind of see when you're training these models. And then in the same way, we can then also plot our accuracy. So as this goes down, our accuracy we can see it goes up as well. And then there's some slight divergence here between training accuracy and validation accuracy. And this is kind of what you're looking for as well when you're trying to decide how many epochs to train on. So you might want to stop somewhere around here to prevent overfitting. Because I think I executed all the cells in the notebook, so I'm going to stop executing it and I'll just look at the outputs. So what we're doing here is so in our training loop, we were only calculating accuracy in small batches. So what we're doing here is calculating it for the whole data set, for all three of our data sets, but for all of the batches in the data set. So after training, as you remember before, our accuracy was pretty low. It's around less than 50%. Now we're doing a lot better. So our accuracy shot up to 97% for training and validation. And on test accuracy, we're at 95%, which is also, it indicates that the model is slightly overfitting, but it's still pretty good. And then author also talks about, some of the things you could, if you get to this point, is you could start doing some hyperparameter tuning. So you could, for instance, change the drop rate or the weight decay, in the optimizer. I think loading rate's also a good one to look at. So those are the kinds of things you'd start tweaking if you wanted to improve things. So that takes us to, I think we've fine-tuned the model. I know we're slightly over time, so if we need to stop here, just let me know, or I can keep going.
How long do you think we will take to do the last part or the last two?
Yeah, I think I could probably do it in 10 minutes or less.
For me, if it is like around 10, would be nice, and we cover the whole chapter.
Yeah, and you will have the recording if you have to drop off. Okay, so now that we've trained the model, we can actually start using it as a spam classifier. So I think this is also often an important step with machine learning, where you don't just want to look at metrics, you want to see what the model does with some actual data. So we create this classify review function. And what this does is it takes care of all of the steps for us to take some raw text that we input and do classification. So I'll step through it real quick. The first step is to set a model into eval, which means we're not in training mode. We'll get a list of input IDs using our tokenizer. We calculate the context weight, so the context length using our positional embedding. And then we'll truncate sequences if they're longer. So if we send in text that's longer than maximum context length, we'll just make sure to cut off the length of that sequence. We'll do the padding like we did before. And then we'll add a batch dimension because we trained our model on batches and it expects an input of batches, but we're only giving it a simple example. This is important to add a batch dimension. We use Torch Nograd to make sure that we disable updating the gradients. And then finally, we can get a logits by passing our input tensor. And then again, it's important to remember that we're only using the last token. We can get the predicted label, and then we can convert that label back into a text label, which says either spam or ham. So we can try this on some examples. So here in the book, the example that the author gave us is that it says, you've been a winner, and if we pass this into this function, it returns spam. And then we have another example here, which is something that we wouldn't expect to be spam, and it does classify that correctly. One interesting thing that happened to me while I was going through the notebook is that I realized that this example, which is exactly the same as this one up here, the only difference is that you'll see this one has a period at the end and this one doesn't, but this is classified as not spam. So I was kind of surprised by this, and I initially thought I did something wrong, and I had to go through the code to realize that was the only difference. But what this tells me is that maybe, as we saw before, the model is slightly overfitting. So it might be overfitting on our training data too much, and this is why we're seeing this. Or it could be that maybe it's learning or it's relying too much on punctuation. So one of the things that I haven't had time yet, but what I wanted to maybe try, or maybe if someone else is interested, is to remove punctuation from the data set and see if this problem goes away. But to me, this is also a good example of why you want to not just look at evaluation metrics, but also look at what your model is doing. And then finally, we have this model, and we can, instead of having to retrain it every time, we can save it like we did before using this function. And then once we save it, we can load it back up and then use it in inference as we want to. So that's it. Yeah, that was basically the chapter. Just a quick summary is that I think the important things to know is there are different ways to do fine-tuning. We only talk about one here. The way that classification fine-tuning works is just by replacing that last output layer with this much smaller classification layer. And then instead of predicting the next token, what we're doing is we're optimizing for this accuracy metric, but we still use the loss function to optimize our model. And then we can use this training loop and way to classify a model to optimize it as we go. Any questions or thoughts, comments?
Thanks for the explanation, very concise. Yeah, this type of fine-tuning for classification is like in the industry is used a lot, like in the spam detection. Also, I don't know, document classification, even like resumes, portals where you apply for a job. Some portals like have a model in the behind the curtains that already looks at your resume and maybe puts it in a bucket of okay, let's continue to the next interview or how to like deny or something like that. Stuff like that. So pretty useful and nice. Then before going, I think we need to pick the volunteer for I don't know where is my for the final chapter. Anybody wants to do chapter 7? That is fine-tuning, but in this case for instructions, right? I think correct. Continue to follow instructions. Any volunteers? No?
I might want to give it a try.
Sorry, who spoke? I didn't see.
Yeah, I'm Shubham. I might want to, sorry, I might want to, try for like chapter 7.
Okay, cool. Shubham does chapter 7. Which way is the best way to reach to you in case you need any help during the week? I can help you
I'm on Discord.
on Discord, but with the same handle like username.
No, it's, I think, let me just
Maybe
check
you
what
can,
the email is.
yeah, you can comment on chapter 7 that you take over and then you need any help, I guess, or contact you there.
Sure.
Before we
Nice.
all sign off, can I just ask, And I guess this is a group discussion, not just aimed only at Santiago, because he's our fearless leader driving us through this amazing learning opportunity. But once we finish next week's chapter 7, how are we going to continue? Does everybody like how we're doing this? Going over code? Is this working well for folks? And should we jump in with another book that is code heavy, or Chip Huen's AI engineering book, which is not quite as code heavy, but it's important framework and whatnot, and how quickly can we go through it, things like that. Well, Santiago, do you want to have that discussion later next week at the end of chapter 7? Maybe we can block 20, 30 minutes where everybody just jump in with your own favorite resources and let's have an open conversation on what we can do. Nobody knows yet, we don't know what everybody else already knows, and there's so many tools out there. I shared one on Discord under the general tab a little while ago. There was a question, what should we do for agentic AI, which is what everything's about. That's where 2025 is all about agents. At least the first half of 2025 will be all about agents. So how do we take what we've learned and begin to develop it even further? So this one I found that Google Docs is that first link right at the top. This Panversity doesn't seem to charge anything, but this Google Doc right here that's being shared on the screen, if you scroll down, this one starts to get into here's how the curriculum's set up. Here's some links, learning materials, et cetera, This works. Now, again, I don't want to drag us all into this discussion right now. We can table this to after we complete chapter 7.
Yeah, I think we can save some time next week and discuss. Maybe this gives us time also for other folks to gather ideas of books that they want to
Mash, do
bring
you
to
know
the table. Yeah.
Do you know if this resource covers something about multimodality? Because it's something I'm quite interested, but I'm looking for resources and I haven't found many about it.
I'm with you. And in fact, even as Michael was explaining it a little while ago, that whole approach, I think multimodality is just an extension of how Michael was explaining. Just take all this data and it's whatever type of signals you put in. If you go with what Jensen's keynote basically said, the foundational AI model, that transform-based architecture, all it's saying is so far everyone's using it with text data. But why stop there? Why not add the physical computing, robotics data, and everything else? So now it's that same model architecture that enables that multimodality with images and so on. There is one book similar to Sebastian's book. This one is called Hands-on Generative AI with Transformers and Diffusion Models. It was published, dated this year. We'll cover this next time. Look it up. It's written by a bunch of folks from Hugging Face. Those are some of the things that we can probably discuss. But Carlos, spot on, 100%. I think agents, multimodal models, those sorts of things are what we should all be thinking about. But I'm going to be quiet now.
Good. Nice idea. Great. Thank you for bringing it to the table. But yeah, maybe let's start posting during the week on general, all the books that we would like to check with you. And then next week we kind of gather the vibes of everybody to pick one. Good.
And Shubham, thank you so much for jumping in to do the last chapter. Your bravery is very commended.
Yes,
Thank you.
Thank you. Thank you. All right, then that's it. Thanks, Carlos. Thanks, Michael, for today's session and see you next week. Have a
Yeah,
good
great,
Sunday.
guys.
Thanks,
Thanks.
everyone.
Bye.
Thank you. Bye bye.
See you.
See you.
Have a nice week.